Hello, everybody can hear me? Okay, good. All right. So about the assignments, so they're graded. I'm a bit surprised about the grades. I thought it would be a bit higher, but so I trust Sati that she graded the way she graded. For the midterms, I'm going to see how things are going. Yeah, so you can email her if you have questions about your marks. If you click on the assignments, I also have posted the solutions. So in some instances, like in questions about sets, I have suggested many different solutions if there were, because there are many ways that you can write the same thing in maths, or any way is fine, as long as it's the right answer. Yeah, so I inspired myself with, yeah, so it's satisamani@gmail.com. Did you get the message I just sent previously? Maybe not. Yeah, and the answers are posted. If you click on the assignment, then they're just, I posted a few minutes ago. Yeah, I was a bit busy. All right. So about the midterm exam that's coming in 2 weeks, if I'm not mistaken, yes. So it's going to be about chapter 1 through 5. So it means everything we have seen so far until probably today. So I think it's a perfectly fine cutoff, because until today it was set theory and linear algebra and functions and stuff like that. And then next class, we're going to start yeah, derivatives and optimization and all of these things. So it's sort of linked, but not all that much. So yeah, so 1 to 5 is a good cutoff. Haven't decided yet how long I should make the exam. There is so much material. Yeah, it's crazy how much we teach you in a few weeks of this class, and still it's just not that much. You're going to see much more later in the next math class, but yeah, that's what it is. Question about where we are, where we're going, about the assignments? No, all good. All right, so let me share my screen. Okay, so today we're finishing chapter 5, hopefully. I'm pretty sure. So there are, at last, so we've kind of caught up to where we should be. Yeah, we don't have to run all that much, but still today's material is a bit tricky, so be sure to follow along quite well. Yeah, there was one thing I wanted to talk about just before talking about the rank. So we were talking about the row echelon matrix. So we finished with A4. So matrix A, just a reminder. What was the initial matrix? Oh yeah, A1. That was 1, 2, 3, 4, 5, 6, 7, 8, 9. in row echelon matrix, or row echelon form, sorry. So we got E4. No, that was E3. That was, so no change with the first row, we don't need to. Then we got a 0 here, and here we got -3, -6, then 0, 0, 0. So that's how row echelon looks like. So you introduce more and more 0 as you go down the rows. This should inspire you what you're doing when you're solving systems. So what you're doing is you're saying, okay, I'm going to use one equation to substitute in all the others and get rid of one variable. So what does that mean? What does it mean getting rid of one variable in my equations, having 0 coefficients on it? And then you're doing the same thing using what you had previously to get rid of more variables in the third equation and in the fourth equation. So this is a matrix version of this process. Yeah, so I've already posted it, so I'm going to post it again. It's set sum at okay, that just yeah, I think I didn't make any mistake. Okay, should the -3 be 1 for row echelon? Yeah, okay, so good. So that's exactly where we're going. So perfect. So here what we did is we used equation 1 to eliminate the first or row 1 to eliminate the first element of row 2 and row 3, then row 2 with a 0 there to eliminate that element. And we found out that, we got zeros there. So what we inferred simply from doing this is it looks like our matrix was not full rank. We're going to define more precisely what full rank is. Now, question from Patrick, shouldn't the -3 be 1? No, well, we're going to go there. So now let's define the next step, reduce row echelon form. So this row echelon form is not unique. Yeah, the row echelon form. Matrix is not unique. But then we have this second concept, reduce row echelon form. So what it is. So I could, for instance, manipulate this to have different set of coefficients there. As long as I have zeros here, that's fine. Okay, so if matrix A is reduced row echelon form, then as suggested, each pivot must be 1 and all elements above pivots must be 0. What are pivots? They are the first element of each row that are non-zero. So that one, and there is no pivot for that final row. So let's do it. How we got the zeros? Okay, yeah, I'll do it again. And how can we get the zero? So A2, to get the matrix A2, what I'm going to do is, what I want is to use, yeah. So use cards. English. So that's something we just did last class. So for instance, getting the first zeros in the first column. Somebody remembers? Okay, it's good that we do that. So to do it, so what am I allowed to do? I'm allowed to add to flip rows, so to interchange this row from that row. And I'm allowed to add multiples of rows to some other row of a matrix. So for instance, what I'm going to do to eliminate the 4 here is I'm going to add to the second row -4 times row 1. And what am I going to get? Then 4 minus 4, 5 minus 2 times 4, 5 minus 8, and 6 minus 3 times 4. So 6 minus 12 minus 6. So add -4 times row 1 to row 2. And for the second one, I'm going to add -7 times row 1 to row 3. So A2 is going to be equal to -4, and then -4 times 2, and -4 times 3. And here is going to be -7 times 1, -7 times 2, and then -7 times 3. So I get what? I get 0, -3. And this is -12, so -6. Here I get 0, so -6 again. What's that? -12. Right? And then what I have to do is add. So now I have zeros here. So whatever I do, when I add some multiple of this row to the last one, then I'm going to get 0 multiplied by something, and I don't care about 0. So it means I'm not going to mess up the first effort I did to get a 0 here. You see? It's like if you solve a Rubik cube and then you solve something, but you're sure you're not going to destroy the work you did in some other phase or some other I don't know if you guys have learned how to solve the Rubik's cube. So and note that I named it differently. So this is a different matrix from that one, but so it's allowed for Gauss-Jordan elimination. All right, so step 3. So that's You could say step 2. Column 1. Yes, so sorry, that's column 1. Step 1. And then step 2. Column 2. So why column 2? Because now we're dealing with this thing. So what should I do? Exactly, -2 times row 2 to 8. So add -2 row 2 to 3. And I get -2 times -3 and -2 times 6. What do I get? I get, so here, of course, I get 0. That's the goal. And here, plus 12. So 0, 2. So that's how I see that I got a problem with this matrix. That when I try to eliminate variables, I'm going to lose some rows. So it means that the rows were collinear. Yeah, that's what we have. Yes. And now what we want to do is simply have a cleaner way of expressing this matrix in the Roshan form. So let's do that. So what we're going to do is yeah, first thing, so what we're going to do is first make sure that the elements above the pivots are, yeah, or we can do whatever we like. Maybe it's easier to start with having a 1 here. All right, so what we can do is, so step, I guess step 3, but you know, depends where you are, depends what's the size of the matrix. So what we're going to do is multiply. Oops. Oh, 2 by -1/3. So we get the matrix A4 this times -1/3. So here I get, of course, 1. And here the minus signs disappear. I get 6 divided by 3, that's 2. Right? Then step 4. Now what do I have to do? I have to get rid of this 2 here. So what should I do? Somebody wants to row 1 minus 2 times row 2. Yes. 1, yeah, add minus 2 row 2 to row 1. A5 equals, so I get -2 times 1 -2 times 2. Oh yeah, I've started having problem with my mouse. I hope I don't. Okay, so this is 0 and this is -4, so -1. And we're done. So in case we didn't have a 1 here, then we would have to multiply some by the multiplicative inverse to get 1, 2. So here we go. And what's neat about it is, so let me just confirm that I get the same thing. Yeah. So note the row echelon form. Yeah, reduced. Row echelon form is unique. And can I do something more? Well, no, because the only way of getting rid of this 2 and this -1, oops, yeah, that's my mouse, would be to have some non-zero element here. Since I have 0 element here, whatever multiple of this row I add to these, doesn't matter, it's not going to disappear. So here, question. If and you're going to see later that this is linked to computing inverses. So if A was full rank, what would its reduced row form? Yes. Answer the identity matrix. So it would mean that here we wouldn't have a 0, we'd have some number, and then we could start by making this number 1, then using this 1 to get rid of the -6 and the 3, because we have zeros here, and then we would have, so that's how you get an intuition of why the reduced row echelon form is unique, because in a way, for any, well, in the case of full rank matrix, you know it's unique, it's the identity matrix. There's no best thing you can obtain from that. So why use the reduced row echelon form? Well, it's, I don't know all the detail about it, but yeah, there's this nice property that here you really have everything you need to know about the matrix. And also, as you're going to see later, the process of getting this row echelon form is a reduced row echelon form is exactly the same process that we would use to compute a matrix inverse. That's where we're going next. Okay. So
sorry, I just have a quick question. What
yeah,
does if A was full rank, what does full rank mean here?
Okay, rank of a matrix. That's what I was about to write.
Okay.
So perfect question. So full rank here would mean that I don't have a row of 0 there. So if it's a 3 by 3 matrix, then its row echelon form would be 1, 1, 1. It would mean that I don't have any row that's linearly dependent on the others, so I wouldn't get the 0 there. So you see that in a way that's a matrix form of eliminating variables and finding unique solutions for my coefficients in a way, because I would have some other stuff on the other side, the row of constant, column of constant terms. So what we're doing here is essentially we're finding that, oh, we cannot find a solution. So maybe if it was a 2 by 2, maybe we would have an infinity of solutions or no solutions, for instance. Yeah, so a full rank matrix means if it's a say it's a 2x4 matrix, then it has a rank of 2. So you don't have a row of 0, for instance. You don't have waste in your matrix. So let me be more precise now. Let me just define all the properties of the rank of a matrix. So the rank of a matrix is defined as the max number yearly independent rows or columns in the matrix. We write it R of A. And so some properties, so R, so if A is m by n, then the rank of A will be smaller or equal to the minimum of m and n. What does that mean? Well, for instance, if my matrix is so like this, for instance, and I have numbers there, then here I wouldn't, if I don't have if I don't have zeros there, I wouldn't say that it's a rank 4. I would say, okay, so here I have 2 rows, 2 columns. So the maximum rank that this matrix can have is 2, right? Whereas if I have this, then the maximum rank is also 2, because here I have fewer rows than columns. So then the maximum I can get is 2. But I could get 1. I could get, if I could do the row echelon or the Gauss-Jordan elimination and get row echelon form, and maybe I get 0, 0, 0, 0. So maybe I get a rank of 1 if I'm unlucky. So that's what it is. A matrix AMN which has rank of A equals to the minimum of MN. I'm just finishing my sentence. Is characterized as full rank matrix. Means if I do the elimination, I'm not going to realize that some row was superfluous and it's just zeros. So in a sense, there is no difference between this matrix and a matrix with 10 other rows with zeros in it. There's no information in that. All the information is stored in the first 2 rows. Yes, there was a question.
Yeah, so does it mean like the quickest way for us to find the rank of a matrix is to reduce it, and if we find the identity matrix, we know that we don't take any rows off, but if we find one row that is full of zeros, we take off one. If we find two rows full of zeros, we take off two, and so on.
Yeah, and also that would mean that imagine you start with a matrix like this. So yeah. All right. So okay. So let me add stuff. So it means so best way to find. Best way to find the rank of a matrix. So for instance, so you have, yeah, let's say I have a 4x2. So 1, 2, 3, 4, yeah. 4, 5, 6, 7, 8. So first thing you realize that, oh, I have just 2 columns and 4 rows. So its rank can be at most 2. So I'm not going to perform Gauss-Jordan elimination on this. That doesn't make any sense. So I'm going to first take its, so 1, make the, yeah, if the matrix has fewer columns and rows, take its transpose first. So you would work with this one. And then you get this. Then to perform Gauss-Jordan elimination. So now you know that, okay, you're not wasting your time. The best you can get is realize that you have 2 rows that are not linearly independent. And what would you get here? So imagine I have this, I have no idea. So I get, so let's do -2 minus 2 times 3 minus 2 times 5 and -2 times 7. So that would be A, for instance, A0. A1, then A2. 0. And here I have numbers, so I know that it's not -2, -4, -6. So rank is 2. So you know that you have a full rank matrix. So matrix is full rank. All right, so back to other properties. So we use the row echelon matrix to find the rank of any matrix. Yeah, so the max, I'm a bit restating the same thing, but just to be clear, the maximum number of linearly. Independent rows in a matrix is the number of non-zero rows in its row echelon form.
Professor, I have a question.
Yeah.
So for the row 2, is it not possible that we divide the row 2 entirely by 2? And then we, yeah, so it'll be 1, 2, 3, and 4 in place of 2, 4, 6, 8. And then we actually reduce the row 1 from it.
Yeah, perfect. It's the same thing. So that's a perfectly good way of doing it.
Okay, perfect.
Yeah, so if you think about what does that mean? So in the first case, I would take the first equation and subtract -2 times the first equation to the second. In the second case, what that means is I start by saying, oh, maybe I should rescale the second equation, and then I'm going to start working on it. So it's perfectly valid. All these are just echoes of what you already know how to do when you're solving systems of linear equations. Yeah, the maximum of linear zero rows in its echelon form. So then what does that mean for the inverse? If E is a n by n matrix and the rank of A is n, so it's full rank. Then, so what do you think it means for the determinant? If you remember. So if I'm saying we're in trouble if we have, so remember that. If we did compute the determinant of this matrix, what would the determinant be? Yes, Patrick, 0, because what I could do is take the third row, and then the determinant would be 0 times the determinant of this, plus 0 times the determinant of this submatrix, plus -0 plus 0 times the determinant of this matrix, so 0 plus 0 plus 0, so I get a determinant of 0. So of course, it means that if the matrix is not full rank, then my determinant is 0. But conversely, then it means that determinant is not 0 when the matrix is full rank. And the inverse exists. Therefore, the system AX equal D has a unique solution, which is what? X equals, well, I just multiply by minus A in front of it, so I get A minus 1. So this is what we're going to do now. Learn how we compute A minus 1. Then one useful property for the assignment or for homework or something, I don't remember that there's a question in which that's helpful for. So the rank of a product of a matrix is smaller or equal to the minimum of the rank of A and the rank of B. Yeah, I could give you a small, quick illustrative example. So imagine a rank 2 matrix. A is let's see, A, B, C, and D, or let's say A1, A2, B1, 2, and a rank deficient. So let's say rank 1 matrix B equal. So I'm going to have C1, C2, and here I just get zeros. Then what is AB? AB equals to, then the A2 doesn't, so what you see is if I take the product of the first, the first row with the first column, I get A1, C1. So you see that the A2 disappears because it's multiplied by 0. So I get here A1, C1. And here I get A1, C2. Here I get B1, C1. Here I get B1, C2. So the fact that I got zeros here sort of nullified these two elements there that I had. So even though the matrix A was full rank, it doesn't matter. I could have had zeros there and still gotten the same thing. So basically now I have, and you can see that, so I have C1 and then C2 and A1, A1, B1, B1. So the row 2 is just a multiple of row 1. So where row 2 of AB is, so what is it? It's row 1 times B1 divided by A1. So AB has rank 1. So you see that when I get the rank deficient matrix, then the other has rank deficiency too, or I lose information. That's what it means. Well, I can give you an exercise to do at home. Compute. Just to convince yourself. So instead of AB compute, AB prime. Find its echelon form. You're going to see that again, you lose information. Okay, so question about the rank and all this stuff. Why do we use it? If not, I'm going to continue with matrix inversion. If you have other questions, you can ask them.
Sir, how did we get, so AB has rank 1 instead of it being 2?
Oh, let's compute it. So let's say matrix M 1.
And the rank 1, does it mean that there's only one row with values in it and the other one is zeros?
Yeah, the thing is now this is not in row echelon form. So imagine that I have M1 that's this, right? So let's compute the row echelon form of M1. I just named it M1, that's just a name. So what can I do? So suggestions. So here it's always the same. I want to get rid of this and have a 0. So what I'm going to do is, yes, exactly. So row 2. Yeah, so add row 1 times. So B1 C1 divided by A1 C1. Yeah, it's even faster than that. Yes. So yeah, you see. So I could start. I can multiply rows by a scalar too. So first step. So divide row 1 by A1 and divide row 2 by B1. So we can really see already. So I divide row 1 by A1, I get A1 disappears, and then B1 disappears, B1 disappears. And then of course I can so add -1. Row 1 to row 2. So I'm going to get 3 equals 0, 0. Yeah, I shouldn't go too fast. So for me, I see it right away, but yes, it's we're learning there. So is that all right?
Yes, sir.
Yeah, so again, yeah, it looked like all the information that was stored in matrix A, matrix A is got kind of lost in the way, and all I got was what I had in matrix 2, which is very sad indeed. So remember this property, it's useful for one of the exercise. All right, matrix inversion. So we've been talking about inverses for a while, but I've never told you how we compute the matrix inverses. So let's go ahead and do that. So again, like computing determinants, computing the inverse of a very large matrix is a daunting task. At some point, my computer is just going to die if I try to do that on a very, very, very large matrix. So it's active research to find ways of solving linear systems in an efficient way that's useful for so many fields of science. So yeah, personally, I've done some research on it too. So not for linear systems per se, but nonlinear systems. Yeah, and you have conjugate gradient method. So LBFGS, so a ton of ways of doing it, which give you numerical approximations of inverses, or rather numerical approximations of solutions to systems. But now let's just go ahead and find analytical solutions, so exact solutions. We start with this. All right, so using Gauss-Jordan elimination. So as we were saying, let's start with the system. So we have a system. AX equals B, right? So A is the matrix of coefficients. X is the, just a reminder, A matrix of coefficient. X vectors of variable. And B vector of constants. So that's our linear system of equation. And now what we want is find a solution. So in matrix form, that's how do we compute the solution? So let's just multiply it by the inverse. We pre-multiply by the inverse, both sides. So I get what? I get A minus 1, A equals to A minus 1B. And of course, this is the identity matrix. Oops. And the identity matrix multiplied by X still is X. So this is my solution for, tada, solution for X. Of course, all the challenge is computing A minus 1. So how do we do it? Well, what we can do is simply do the following. So we do Gauss-Jordan elimination on both sides of the equation. So 2 by 2 example. let's perform Jordan on both sides. So what I have here is A1, A2, oops, P1, P2, that multiplies X1, X2 equals then A3, B3. So that's my system. But note the following. This is exactly the same as one, zero, zero, one. Because if I compute, I multiply this identity matrix with this vector, I get this vector exactly. And what I can do now to respect to make sure that things are equal on both sides is perform Gauss-Jordan elimination with the same steps on both sides of the equation. And this is exactly saying that I have I'm looking for solutions there. And so if I say use some equation and add it to some other equation, then as long as I do it on either side, then I'm not changing the value of my solution in the end. Step one. So let's subtract. Yeah, add. Every time I could write subtract, or I can add minus. So what do I want to do? I'm going to go do Gauss-Jordan again. So minus B1 divided by A1 times rho 1. To rho 2. So what do I get here? So let me be systematic. This is times A1 times A2 times 1 and times 0. So that's not too difficult. So I get, oh, my mouse is giving me a hard time. Okay. So minus B1 divided by A1 times A1. So that's, of course, 0. That's what I wanted to do. And here this, this I get A1, P1, A2 divided by A1. Doesn't matter where we put the A minus. You mean here? I'm not sure what the question is. Anyway, let's continue, and if you think about it more, tell me. Okay, and then this is just 1 again, because minus B1 divided by A1 times 0. So I still get 1. All right, so I got rid of this. Now what could I do? Let's, now I want to get rid of this A2 there. So I'm going to add minus yeah, maybe I should make sure that this is the same the same yeah, this 0 is there. Yeah, let's work on that a bit more, because otherwise I'm going to get a mess of a computation. So this is divided by A1. Okay, so this makes more sense. Then what I need to do, I want to have 0 here. So I'm going to add minus A2 times the inverse of this, A1 divided by P2 A1 minus P1 A2 times row 2. To row 1. Okay, this is times, oh, sorry, it's this. Okay. And now, as I wanted, so this cancels out with this. That's the goal. Then A2 minus A2 becomes 0. Oh yeah, sure. It's just that it's 0. Yeah, you're right. I'm being careless here. Times 0. I'm not sure what you're saying. Okay, so what you're saying is, given that I already told you how to compute a 2x2 inverse, why would we use this method? So thing is, I haven't told you where my formula for the 2x2 inverse comes from. And here I'm showing you where it comes from. It comes from exactly that. But good point. Of course, in the end, I'm not going to tell you use Gauss-Jordan elimination each time, but you could do this, do it this way. It's almost exactly the same as just solving the system by yourself, but it's like very tedious to do it, but it's good. And of course, I'm not going to do it for a 3x3 or 4x4. We're just going to see where the formulas come from. Okay, so this, I get this. Okay, so what can I do with this mess there? Here I get A2, A1. So here I get the plus this is there. A1 gets cancelled with A1. There's a B1 there. And I'm just going to do some step-by-step way so you don't get too confused. I'm just going to leave it that way and then simplify this further. So here I have this plus this. Okay, minus B1, A2 plus A2, B1. So these two disappear. I get this. This thing goes there. Let's put the A2 in front. Okay. Almost there, almost there. Now, multiply row 1 by what? By 1 over A1. And so here what I'm doing again is I want to get 1, 1 and row 2 by this mess there, E1 over B2 A1 minus B1. Here I get this. I'm not going to do it for a 0. I'm lazy. So of course, by design, this is 1. This is 1. So we're done on that side. And when the smoke clears, what do we get here? So A1 disappears from there. A1 disappears from there. And then this stays there the same. And A1 disappears from here. So I get minus P1. All right. And can we simplify this even further? So on that side, we get, since it's the identity matrix, I can get rid of it. And here what we have at the denominator, it's all the same, B2A1 minus B1A2, B2A1 times minus B1A2. So 1 over B2A1 minus. And here, if I want a solution, I just get x1 equals to B2A3 minus A2B3 divided by B2A1 minus B1A2, for instance. So is it magic? Well, it's not magic. It's just very tedious, in my opinion. But it's good that we see where it comes from. So x1 equals B2 A3 minus A2 A3. And x2 equals to minus b1 a3 plus a1 Yeah, it can be easy. If I'm being nice with you in the exam, and I'm giving you numbers that are not too hard to work with, then yeah, it can be easy to do. So that's my matrix here. And of course, this pattern there is going to repeat itself. So now I'm just going to tell you, I'm not going to prove you, but I'm going to tell you what the general, so first of all, somebody recognizes that, I hope. Well, I've already told you before. No? What is that? Yes, thank you, Mr. Jacobi. Yes, I'm going to give you something with sines and cosines too, and all this wonderful thing. Okay, so general formula. For an inverse. So here you don't need to use Gauss-Jordan anymore, unless I tell you to, and I want to see your steps. But yeah, they can be quite, as you've seen, that's just a 2x2. And yeah, since we didn't have any numbers, but of course, if you have numbers and they cancel out easily, then it can be easier than this. So I can just write it in a few symbols. So for a matrix. A, that's n by n. So A minus 1. Oops, well, why did I write it there? I don't know. Is equal to 1 over the determinant of the matrix times, here I'm going to write what each cell is, or what each row and column is. So it's minus 1 times I plus j to the I plus j times the cofactor AI j. But transpose, that's the tricky thing that you have to realize. So it really looks like we're computing a determinant. It's just that in the end, we're using a transpose. So I'm just going to define all of this so you know what we're talking about. So where oops, this is the determinant of A and this thing there is the transpose of the cofactor matrix. and I realize it is 10 o'clock. So I think it's a perfect time to take a break. When we come back, all we have to do is compute the inverse of 3x3 matrix that I'm going to give you. And then I'm going to show you about Cramer's rule, which is going to make things for you even easier. And that's going to be it. So maybe we'll have time to talk a bit about other stuff after that, but I don't think so. So questions just before the break? You're going to remember what, oops, my mouse is really nasty to me. So you're going to remember what cofactors are and all of these things. Okay, so let's come back in, let's say 12 minutes. So 10:15, I have 10:03, so you come back at 10:15. And we are back. So rather than tell you in words what all of these things are, let's just give you an example. So as we say, a picture is worth 1,000 words. Well, an example is sometimes worth 1,000 words too. So let's go ahead and do it. So example. So let's have a 3x3 matrix. A is, let's say, 4. Oops, no. Let's have 1, 1, 1, 2, 3, and 1, -1, 1. Hopefully this is not, did I use this example before or not? I don't remember. So let's start by computing the determinant. How do you do that? Well, you go to the menu and you say determinant. Ooh, 4. So that's it, we have the determinant. So you would have to do it yourself, of course, but here I can cheat because I'm the teacher. And now the whole point is to show you what this thing here. So, well, actually, this is almost exactly what you're using for the determinant, but then you're using the transpose at the end. So let's build the cofactor matrix C. So I call it C because after that, we're going to take the transpose of C. So, so I want to have some intermediate matrix. So C will be equal to a big matrix. So we have the cofactors of let's have my cofactors there. Cofactors are, of course, so this is 1. So here, how I do it. First of all, I ask myself, what is it a plus or a minus here? So column 1, row 1. So 1 plus 1. So -1 to the 2 is 1. So here I get 1, or rather, yeah, plus, minus, plus, minus, plus, minus, plus, minus. All right. And then, so they are the determinants of the smaller matrices, which are on the opposite side. So here, well, actually, it's going to be very hard with my mouse. Okay, so here it's first column, first row. So I delete the first column, first row. Here, first row, second column. Here, first row, third column. First column, second row. Second, third. Then third, first, third, sorry. Second, third, then third. Does that make sense? Did I make a mistake somewhere? Just checking. Yeah, I think that's right. Okay, so this is 2 times 1 plus 3, so that's 5. Here, 1 times 1 minus 3, so minus 2, so minus in front, so that's 2. Minus 1, minus 2, so minus 3. Here, 1 minus, and minus in front. Oh, sorry, 1 minus, so that's plus 2, so minus 2, yeah. 0, minus 1, minus 1, minus 2, minus in front, so plus 2. And 1, 3, minus 2, so 1. 3 minus 2 with a minus in front, so sorry, 3 minus 1, sorry, so 2 with a minus, so it's minus 2. And then 2 minus 1, so 1. Oh, so I have the cofactor matrix C. So does that make sense? So every time what we do is, if I want a cofactor of this, it's the determinant of the matrix without that column and that column and that row, and I multiply it by 1 if I have if the number of row plus column is the sum of that is positive, and minus 1 if the sum of that is negative. So that's a neat way of expressing this. And I compute the determinant every time, so I get this. And now the tricky part, that's something that was not there for the determinant, is here we have to take the transpose of C. So the transpose of C equals to, here I get, I'm going to invert these two. Here I get minus 3, here I get 1. Minus 2. So that's the transpose. So then I'm done almost. A minus 1 equals to 1 over 4, the determinant, times C prime. So it's equal to this. All right, and just to confirm that we haven't made a mistake, compute matrices inverse. Oh, please. This is what we had before. So does that make sense? Half minus 1/2 minus 3/4. Yes, good. So that's how you do it. So the thing you have to remember is when you have the cofactor matrix, then you have to take the transpose of the cofactor matrix. which looks strange, but yeah, that's what we have to do. So it's 1/4 times the transpose of the cofactor matrix. That's the inverse. So it looks like a recipe because obviously I haven't proven that you can do that for n by n matrix, but I have showed you that this is what you get for a 2x2 matrix. Here you have for a 2x2 matrix, you have 1 over the determinant of the matrix. And here you have, so the cofactor of, so my matrix was A1, A2, B1, B2. So the cofactor matrix of, the cofactor of A1 is B2. The cofactor of B2 is A1. And then the cofactor of this cell here is minus A2, minus the determinant of A2, which is A2. But then I take the transpose. So instead of being minus A2 here, it's minus A2 here. So that's why I get it here. And same thing, the cofactor of this cell would be, minus B1, but then I take the transpose, so I get minus B1 here. Oh, sorry. Yeah, okay, so again, so you use this expression there. That's just a neat way of expressing what it is. So if it's column 1 and row 1, then you get minus 1 to the 1 plus 1 equals minus 1 squared. So equals 1. So you know that there's a plus here. And here, the second one, the next one, you're going to get a minus because you're going to get minus 1 times 1 plus 2. So it's 1 3. So it's yeah, so it looks like cooking with a formula, with a recipe, but we don't have time to prove everything. And anyways, I'm sure you would get mad at me if I spent my whole day doing proofs with you. All right, so questions about how you can compute the inverse? No. So just practice with the matrices you like, put numbers, compute the inverses, and get good at it. What did I want to say? Oh yeah, by the way, this is not how people solve systems. We usually don't. So when you get older, you realize that you almost never compute the inverse. There are many other ways to doing it. So a very popular way is called the LU decomposition, lower upper, and you express the matrix A as L IU, for instance. Well, where L is some matrix that has that is lower triangular, and U is some matrix that is upper triangular, and then you can solve for X very easily using this this LU matrix there. So this is just what you will learn if you continue learning about stuff in linear algebra. But yeah, for now, let's just say that this is the way you do it. So you compute the inverse, and then you have it, and then you have the solutions right away. Okay, so last topic for today, Cramer's rule. Cramer's rules is a way of making your life even easier. Here it is. So what if I just want the solution to a single variable? So I went, do I have to go through the trouble of computing the whole inverse if I want just say x1 as solution? Well, no, you have a nice trick that you can use, which is basically you can already kind of guess what it is here. So what do we have here? We have the determinant of the matrix A. What do we have here? B2A3 minus A2B3. And I'm going to, even invert this to make it more obvious. So what happened there? B2 is still B2 and A2 is still A2. So it's just that instead of having A2 and B1, you have A3 and B3. So let's look at the matrix, what happened to it. So I had this system there. So at the denominator, I have the determinant of the matrix A, A1 and B2 minus B1, A2. Then at the denominator, I have A3, B2 minus B3, A2. So here that was substituted by A3 and this was substituted by A3. So in the end, X1 is equal to the determinant of this matrix. But this, instead of A1, A2, I have A3, B3. That's just what it is. I have one, I just took the constant terms and put them in the first column. And that's my solution. And what is X2? Well, let's put that in order. So I have A1 here. And B1. So A1, B2 minus B1, A2. So that's the determinant of the initial matrix. And here, what happened? What got changed? Can somebody see it?
A2, B2.
Yeah, A2, B2. But so it got changed to oh yeah, you're right. A2 and B2, exactly. Which was substituted by, again, the coefficient matrix. So this is like this, and A2, B2 was replaced by A3. Again, I'm just showing you that this works for any 2x2 matrix, but then you have to trust that the trick or the formula or the recipe works for any n/n matrix. So let's, oh my, I have to change my mouse. Okay, so let's go back to our Cramer's rule. Yeah, so I have this system there. Yeah, and I know that solutions will be X. X1 equals. So I'm just going to put in bold what I just substituted. Here, X2. And of course, I know that X1 then is A3, P2 minus P3 divided by if I take a 3 by 3, should I do that? I'm afraid I'm going to. Yeah, I don't know if I should do that. What time is it now? 10:39. No, okay, I just wanted to, you can try with 3 by 3 matrix. Find that. Oops. So at some point there, it's a bit tedious as computation. So general idea. So I think you're going to like me for sparing you some tedium. So if I have a n by n matrix, X equals P, to find Xi from the matrix. Yeah. How to find Xi transform the matrix AI by replacing the column by the vector. Then compute. I equals AI divided by E. All right, so let's try an example. So we have, for instance, zero, 1, 1, 0, 0, 3, then 1, minus 1, 1 times is this an econ course? Well, it's a math course, but for economists. So it's both, I guess. So we're going to have some economic example just following this. Solution 1, 2, 3. And I want to find y. Somebody has an idea how I should, so let's just form my matrices. So this divided by this, but now since I want y, so y is the second variable. So I'm just going to substitute the second column by this 1, 2, 3. And then do it, please. Find the solution. If you're smart, you can find the determinants very easily. Think of it, how you would do it quickly. Oh, I forgot my water bottle. Cofactor of y. So cofactors are, so for instance, if I have some matrix here, the cofactor of the last, this element there, which is the last row, first column, is plus the determinant of this matrix. If I have this one, then it's the determinant of, it's minus the determinant of that matrix. Good, Aidan, excellent. So I'm going to tell you the kind of, so I'm now, listen to me very carefully. This is very important. What kind of questions am I going to ask you at the exam? So what I want is to test whether you understand the material. So how I do that is by giving you something which will be easy and done well by people who do understand, and can be difficult and take time if you didn't study properly, if you didn't practice, if you didn't think a bit about what you were doing. Midterm in 2 weeks. Yes, 2 weeks. Yeah, I'm not sure if it's going to be 3 hours or 2 hours or 1 hour. I'm going to decide based on how much material I have. It. There are so many things that we have covered so far. It goes incredibly fast. So I'll try to make it as fair as possible for you. Anyway, so back in what I was saying. So can we have 24 hours? No, that's the trick. Is I'm going to, that's the thing about, okay, yeah, many things I have to say about it. So about the exam. So how this is going to work. So you have, of course, to show your work, your steps, because obviously you could, find some ways of just having the answer, and that would be easy. So I don't want to answer 1/3. I want to show you how. I want you to show me how you did it. You have to be quick. That means, so normally it's forbidden to use material. Did I write that it's forbidden or not? Anyways, it's not advisable. Why? Because it has to be second nature for you to answer these things quickly. Otherwise, if you just think, oh, I'm smart, I'm just going to, okay, open book. All right. So it's open book. But if you think, oh, it's open book, perfect, I don't have to study, and I just get there and take my time, and if there's a question, then I just go in and find it in the notes. This takes forever, and you're never going to finish. So you have to be kind of fluent with the material. So when you see something, you're like, oh, I know how to do that, and so I'm going to test you about the core concepts, of course. But you have to be good with these core concepts. So the thing is, of course, if I gave you a week to do it, then it wouldn't be an exam. It would be just another homework. Right? So yeah, it's gonna. So that's the way I think it's the best to test you. Yes, you upload a PDF of the solution on Moodle. Yeah. And now the kind of questions I want to ask you. Easy if you understand. Difficult and long if you don't. What do I mean? Well, I mean, if I give you some system of equation represented this way, and I ask you what's the solution of y, so if you're not sure, then you may think, oh, well, okay, I remember that this comes from a system of linear equations, so that's the only thing I remember. So let me rewrite everything 0x plus 1y plus 1z equals 1. 0x plus 0y plus 3z equals 2, and then solve it and then find the solution for y. So you could do it this way. It's going to take forever and you're not going to finish. if you are quick, then you think, oh, well, I already have my matrix, let's compute the inverse. But if you are even quicker, you think, oh, well, now I have this extra way of doing it, which is Cramer's rule, which is even quicker than that. So since I just need y, I'm going to insert the column there and then compute the determinant. And if you're even quicker than that, then you might be clever about the way you compute the determinant. Why am I saying that? Because the determinant can be computed using any row or any column, any way you like. So what would be a clever way of doing it? Well, you have 0 here and 0 there. So you know that the determinant of this matrix will be 0 times the determinant of this, plus 0 times the determinant of this, plus 1 times the determinant of this. So so that's a very quick way of doing it. So you know that it's going to be 1 times 3 minus 2 times 1. And here it's going to be, again, you can do the same thing, or let's do this, let's use this row there. All right, so it's going to be then -3, just for fun, just to show that I can be clever and use that one too, times the determinant of this, so 0 times -1. -1 minus 1 times 1. Oops. This is equal to, doesn't like it. So, oh yeah, no, it's not -3 actually, it's plus, minus, plus, minus, plus. Oh yeah, it's minus, all right. Had some doubt. So 3 minus 2 is 1. And this is -3 times 0 is 0 and -1, so 3. So that's 1/3. So that's what I mean by questions that are going to be easy if you have studied well, and if you could spend 15 minutes if you do it in the wrong way, but if you know how to solve it, if you know how to use the Cramer's rule, and you realize that there's a clever way of computing the determinant by using a column or a row with lots of zeros, then it can be very quick. All right. Other questions on your mind about the exam? No? Okay. Oh yeah, let me just put this in bold so we know that this is where we substituted the column. And by the way, Cramer's rule is really what we always, like professional economists. Yeah, it's posted. So you click on the assignment. So I posted it this morning. So you click on it and then you have the solutions. Do we scan our work and to upload it? Yes, exactly. How many questions will be about matrix in the exam? 12 or 15, I'm not sure. No, it's going to be proportional to the amount of time that we spent on it. But know that this is fundamental stuff. Once you are good with matrices, you're good for life. Yeah, so I'd say, I don't know how many questions do I... Yeah, it's a lot of material, so okay, I would find it very surprising if the midterm was just half a course, like half a class, so like an hour and 10 minutes or something. I would find it surprising. Practice exam. I don't have time for that, sorry. But so you see the kind of questions that I do ask in the homeworks, it's going to be this kind of questions. Yeah. So, but sorry, I would like to give something, but I'm just so overwhelmed with other stuff. So. Okay, so last example. So let's go. So somebody asked, would it be possible to more difficult tutorial questions? Well, so you're asking for difficult. I'm telling you, the exam is not going to be more difficult than what you have in the TA sessions. A more difficult question. So if you look at in the books, you have tons of exercises in the book. But I wouldn't say they're necessarily more difficult than what I give you in the TA sessions. It's mostly similar. So it's really, if you're good with the type of things that I give you, you're like good to go for your economist life for sure. I mean, you can. Okay, so let me give you a more difficult questions. Prove that A times BC equals AB times C, where A, B, and C are gone. Is that, did I make a mistake there? Yeah, no, that's right. So meaning you can multiply them. So it took me a while to figure out a way to prove that, but because I couldn't find a proof on the internet. So I guess proof exists, it's just I didn't look for long, but so that's fun to look at. So if you, on your spare time, if you want. So that's a more difficult question.
I wasn't asking for more difficult questions because like for fun, I just said that because I feel like the tutorial and the assignment was significantly more difficult than the tutorials, and it's kind of like, whoa, that's why I was asking.
Oh, okay.
But if you're saying
I would like to say I agree. I found that the questions you were asked in the tutorial weren't like representative of what the questions were in the assignment.
Yeah, so that's why I was asking for more difficult questions in the tutorial, because I don't want to get to the test and feel like, whoa, like what is this, you know? So
okay, no, but so the homeworks is meant to be more difficult because you have a few weeks to do it, right?
but it's kind of just like if we don't have any examples of that, and then you expect us to like pull the answers out of our ass type thing, it's kind of just like it's like a shock, you know? It's such like if we don't look at anything like
okay, so
in class or in the tutorials.
Thing is, yeah. Yeah, so I'm going to be sure that the questions I gave you have similar difficulty levels, or rather I'll see that. So that's a good way to write an exam. A poor exam would be all easy questions or all hard questions, because then you could have catastrophes where everybody has 40% or where everybody has 95% and you cannot discriminate between good and less good students. So this, I'm telling you, this is what I'm going to try for, is to have a few very easy questions, some medium difficulty questions, and maybe some questions that look like what you may have had in the homework, just to show, just to see who's very good at this stuff. Otherwise, that's not a good way to evaluate you.
But like, I'm not specifically asking for you to take the exact same examples from class. Like, I understand that they're going to be a little bit more difficult, but I personally found that the scale, like I feel like in tutorials you'd like baby la la, and then like, and for the assignment you're asking us to like calculate the distance from space. Like it was just very like extremes.
Oh
Even
yeah.
if we had more time to do it, like I really just felt like not
Oh.
comfortable at all doing the assignment.
Oh, so okay. I'm genuinely surprised that you say that. I hadn't realized how difficult that was. Let me go back and look at. Anyways, it's reflected in the fact that the grades aren't that high. So, what is there something that you found especially difficult?
I mean, I would have to check because I don't remember exactly. Like, I tried to like block it out after I was done, but I can like check and maybe send you an email.
Yeah, because personally, I thought I really thought the difficult thing was just the first question, first set of questions on sets. This is really uncharted territory when you haven't thought really about how to express sets. So this I thought was the most difficult, but then solving a system of two equations, three equations and three unknown, but linear, then you just substitute, and that's something that you learn in high school, basically, or in algebra, no?
Well, I feel like the sets was the easiest thing for me. I think asking for like the multi-market partial equilibrium with more than two, because we only did examples with two markets, and then asking for like more markets, I was like, whoa, like I don't know where to go from here.
Okay, well, it's just so you have three equations, so you use equation one to get rid of one variable and to get rid of the same variable in equation 2 and 3, and then you use equation 2 to get rid of, you have, yeah,
But like you know
yeah.
that because like it's your job to know that, but if you never tell us how to do that, then we're not gonna know.
Okay, yeah, no,
Even
but
like the textbook only has examples with two markets, so it was really like
okay, but
not even possible.
but I gave you that in the class, right?
Yeah, but you only gave us two markets.
Okay. Okay, so that's good. Good that you tell me. Really, I'm surprised that you found that difficult. Sorry, that is being disrespectful or anything. It's just
No, I understand.
yeah. Okay, it's good that I know that for next time. I thought that the jump would be very straightforward, but if you say it's not that straightforward, then yeah, I'm going to give some perhaps some yeah, TA's question with this next time. Yeah. Okay, good. So yeah, it's for me. It's not easy to cut. Yeah, my PhD is the closest to me, and then I can kind of imagine how I felt during my master's degree, but then imagining myself starting a university, and then what did I know? What did I not know? It's just sometimes you just forget how much you learned at university. Plus, the level of everybody is different. So some people have more background, some not. So personally, I would imagine that matrices is by far the hardest thing you have to learn, because it's just a totally weird way of doing stuff with squares and all these rules that you just discover. Plus, it goes very fast. So whatever question I give you with matrices, they're not going to be too difficult, I hope. All right. So anyways, I'm going to look at what you did and adjust. Oh yeah, and the computations were a mess. Okay. Okay, yes, so that's something too. So that's on me. I tried to have numbers that worked, but in the end, it failed horribly, and the numbers didn't add up, and even I made a mistake in the solutions, And Sati said, "Oh, but by the way, your solutions are not right." And I checked that again, and I was like, "Oh yeah, I made a mistake somewhere." So yeah, it's normal that they were a mess given what I gave you, but it was not my initial goal. I hope that things would behave a bit better. Yeah. So yeah, especially during the exam, carrying like many digits or weird fractions. Yeah, I want to make things feasible and not tedious. So yeah, okay. That's the other rules is questions shouldn't be too tedious. Because if you have some question that requires 15 steps to go perfectly, otherwise you get it wrong, then nobody's going to get it right. That's the rule number one of exams. We make mistakes along the way, and our solutions are never perfect. So I'm going to make questions that can be solved by thinking about them and doing a few arithmetic operations, maybe a bit more if I have to, of course, but that's what I'm going to strive for. So I'm not going to have you just, oh, it's like let's see how many digits they can carry and not make a mistake somewhere. No, everybody's going to make a mistake. I can make a mistake for sure. Okay, so Anthony, you say question 3 and 4 seem the most out of whack difficult. So what was question 3 and 4? Wow, okay, well, yeah, to be fair, really, I didn't think it it would be so so difficult, but oh yeah, 3 and 4, right? So yeah, 3, it's on me. I wanted things to work out better than they did, so but I didn't set it up right. 4, I mean, and then 3 was. Oh yeah, okay, yeah. This okay, I can see that. Yeah, it's it requires you to make extra steps in your head. If I ask you, does this have a solution or not? Then you just compute it and you see whether you lose an equation or whether you find 1 equals 2, for instance. So you know that that there's no solution. Then if I tell you, oh, there's A and B, and what value of A and B should you get to not have a solution or have an infinite solution? Yeah, that requires some extra thinking. Okay, I can see that. Yeah, go ahead, Patrick.
Yeah, I was just gonna say, if you were looking at what it took to do the assignment, I did questions 1, 2, 4, and 5 all in one sitting. And I'd say that maybe took me 1.5 classes. Whereas question 3 was abysmal for me.
Oh yeah, okay.
I was like spending a day and a half trying to solve it, and I knew I wasn't going to get a good mark on that question.
All right. By the way, you could work in teams, right? But it's good that you work alone because you that way you're sure that you get exposed to all the questions. Yeah, all right. So I'm going to be frank with you. What I did is so Sati shared with me some of the material of last year. And so this looked pretty much like what was asked last year. So what I'm guessing is the teacher was hard on her students. So I thought, okay, I don't know their level, but it's probably it's well calibrated for the level of second year students at Concordia. So I felt okay. Yeah, it seems a bit strange, but if she deemed it doable, then it's doable. But yeah, now I see that it was more difficult. It's adjustment. It's the first time I give the class, so I'll take it into account.
No, I'll just say this, and if you were to ask me to rank the parts, I'd say C was the hardest. As soon as I read it, if AB equals 6 and A does not equal 3, showed that the system will be inconsistent. It was like I didn't do well on the first two parts, so I couldn't carry my work through to
Yeah, all right.
show C.
Yeah, all right. So C, the only thing you had to do is say, okay, AB equals 6, so I can whenever I get AB, I can substitute it with 6, and then I can put whatever other value for A, and then show that I get something strange with it. So yeah, okay. Thing is, okay, I never told you this is how you should do it, but I let you sort of figure it out for yourselves, and that was a challenge. All right.
Yeah, that's what I did. When I saw AB, I put 6, and when I saw A, since I knew it didn't equal 3, I said 6 over B. So I had my equations all in terms of B.
Oh yeah, but so I mean, if you have AB equals 6 and A doesn't equal 3, but A could be equal to 5 or 0, no, well, maybe not 0, but so yeah, 1 because anyways B is going to be equal to 6 over A. So it's going to make up for it. Okay, but yeah, I see. It's actually, I'm glad that it made you work a bit and think about it. Maybe more than I thought it would, but yeah. All right. Okay, so and then question 3. Okay, yeah. So about if you think your solution might be good, the thing is, there's so many different ways to show something or answer something. I gave when I could, I gave multiple ways of doing it. If you discuss with the TA and she says, "Oh, I don't agree," but then you say, "I don't agree with you," then of course, so I'm just going to look at it and decide whether it's good or bad. Generally, I would like her to deal with it, because if I start grading a second time, I'm going to introduce a lot of bias, and I don't want that. So she graded it. But yeah. What do you think about this answer? Yeah, I have to think about it. Okay, well, write to me in private so I can have a trace of your question, and I'm going to think about it. Yeah, I can't answer right away. So yeah, it might be good. By the way, I'm talking about the suggestion of in the chat. Okay. Right. So do we still have time to do some small exercise? Yeah, I guess we have. So let's go back to. So this is really if you have nothing to do over the weekend. it's fun. It's fun to think about it. It has to do with how summations work. So if you are able to solve this for any matrix, then you have my utmost respect. So a small example, national income model. Yeah, so somebody was complaining there's not enough economics, so let's go back to it. So I have, so that's the same Keynesian thing we had so far that you may see in macro someday or not. C G0 and C equals to A plus BY. So let's solve this using Cramer's rule. All right, so first of all, we have to decide what's a variable, what's not a variable. So what are the variables there? Well, we know I already asked. So variables are Y and C. So we are going to express this as a system. So times. Okay, so our two variables are Y and C. Yeah, so first of all, what we can do is put all what's to do with the variables on the right and left hand side, and then leave the constant term on the right hand side. So that's easier. So here I get minus C. Here I get minus B plus. So here it's structure. So you know that the first variable, all the coefficients are here. The second variable, all the coefficients are here. And these are all constant terms. So you can just put that in your matrix. Oops. So this is 1 minus B, 1. Then, oops, no, that's not why I didn't know why. Let's see. Did I write it with K before or not? Ah, no, that's not with the K, that's with the C. Let me just Google it real quick to make sure I'm not, I'm writing it properly. Yeah, it's Cramer's rule with a C. I don't know why I wrote it with a K. All right. So I'm going to do it for Y, and then you do it for C. Y equals to and this is the first variable, so I just substitute my constant here. Okay. So what do I get? I0 plus G0 times 1 minus A times minus 1, so plus A divided by 1 minus B. All right, so you do it for C. Nobody has an answer? Oh, some questions. Sorry. Yeah, I think that's right. Well done. So let's go ahead and do it. So I take my coefficient matrix. And then I put this at the second row. So I'm going to get A plus B times I0 plus G0 divided by same thing, 1 minus B. So yeah, you got it. Anthony, there's a small parenthesis missing, but I'm sure you had the right answer in mind. All right, so that's about it. I could start talking real quick about comparative statics. But you don't really need it for now. So maybe you can say it's call it a day. It's 4 minutes short. Or I could have, yeah. Do you have extra questions for me? All right, so if there are no questions, well, yeah, again, the exam is going to be up to here, no further. Yeah, 1 to 5. So the term material stops here. Okay, yeah. So y equals the determinant of. So are you okay with this step there?
No, I didn't understand why we have like the income and the government spending, and how did we get that? This cofactor exactly.
Okay, so are you good with this step there?
Yes.
Okay, so yeah, so here what all we do is we want all the terms that have the variables with them on that side and the constant term on that side. And then so I can express it this way. And then what is Cramer's rule? So let's go ahead. So Cramer's rule is I would compute like the determinant of this divided by the determinant of this, but instead of the original matrix of coefficients, this matrix there, if I am interested in the first variable, I'm going to substitute the first column of this matrix by the constant terms. And then so that's Cramer's rule. That's the recipe for saving time. Just turns out that that's how the world works, and it's true. So that you should use it. Yeah, and you get so then you get A0 plus G0 times 1 minus A times minus 1, so plus A. And the numerator this, and then under numerator 1 minus B times minus 1, so 1 minus B. So you might be unhappy with the fact that Cramer's rule is the way it is, but that's really something that if you learn it, it's super useful. Whatever computation you do in life, in economics. Every time I cook, I'm like, oh yeah, how much sugar should I use? Well, let's use Cramer's rule quickly, and I get my solution. I'm just kidding. I don't use Cramer's rule on a daily basis, but in economics, it's useful. All right, so if there are no more questions, I say thank you, everyone, and I see you next week.